Okay, good morning everyone. Welcome back to the course after the holidays. Hope you've had a nice holidays and you're ready to study a bit more. So till now in this course we've seen the idea of the Bayes filter and then how to use this Bayes filter say for the application of localization. We also saw the motion models which characterize how the robot moves over time in the presence of noise. We saw some observation models which tells us where the robot is based on the local observations. So if you have a laser scanner, you can use the information from the laser scanner to figure out where you are. We saw a couple of methods for localization in terms of an extended Kalman filter. We also saw the Monte Carlo localization algorithm. So these filters basically were for the task of solving the problem of localization. Right. We also saw a couple of techniques for doing mapping. So which means given where you know where you are, you make a map of the environment around you based on the observations. Right. Then we saw a little bit about robot control, which told us how to move the robot from point A to point B in the environment. And then lastly, we saw some algorithms to actually find this path. So we saw Dijkstra or A-star algorithm, which showed how to go from point A to point B actually. Right? So in the next 3 to 4 lectures, we'll focus mainly on the interpretation of data. So we'll move towards semantics, which means given some data of the environment, so be it an image, be it a laser scanner or a laser scan. So the question now is, can you make some semantics? So can you use your knowledge and say something about the environment? So take for example, if you have an image of this room, given the image, what can I say in terms of what are the parts or what are the objects in this room? So can I detect that these are the tables, that this is the roof, that there are lots of people in here and so on. So now we want to reason at the level of semantics. So we want to learn a bit more about the world itself in terms of higher concepts, not just that there is a point at some point in the environment, but a bit more about what that point is or what that area of interest is. And so in this, given this context, so the next 2 lectures, so this one and the next one, we'll be mainly studying the problem of classification. So the problem of classification essentially is given the data, so whether it's an image or a laser scanner, figure out what a particular part is. So this is a door, this is a table, and so on. And so we'll see some basic techniques of how to do this. So today we'll see a couple of basic techniques, and in the next lecture we'll expand on these techniques, which are a bit more sophisticated and very close to the ones that are used in the real world these days. Right? Okay, so let's start off with a motivation example from the agricultural robotics side. So what you see on the left here is an image taken from a UAV of the field. So there are some plants, there's some soil behind, so in the background. And one of the important questions there is, say if you want to detect which are the regions of the plants, right? So where are the vegetations? The question we would ask is, given this image, so given a pixel in this image, is that pixel a vegetation image? So is there a plant there or is it a background? So this is the question that you want to answer, and if you do this successfully, you would get something like this. So the white parts in the image correspond to the green parts here or the plants here, and then the black ones are the background. Right? So essentially what we have done is taken the input data, which in this case is an image. We asked the question, which parts of this image is a vegetation and which part is a background. And the classification system, so we'll study how to build these classification systems, but once you have the classifier, it should give the answer which parts are vegetation and which are the background. Right? Is this clear what kind of problem that we are going to look into today? Okay, so specifically this kind of classification is also known as binary classification, because the question is a yes or no question, which means that it's a class 1 or it's class 2. So it's either one of the two. And this is a special case of the classification problem. In general, you could have any number of classes. So you could have plants of type 1, plants of type 2, soil, grass, whatever. So mostly in this lecture, we will look into binary classification, which means given the data, we say it's either class 1 or not class 1, basically. Right. Yeah. So to define a bit more mathematically what the classification problem is, so basically we are given a set of classes omega. Right, so omega 1 to omega k. In this case, it's the general classification problem where k, if k is 2, it's a binary classification problem. Then you have k classes and you have something called as the features. So in the previous example here, a feature from this data could be the RGB value of that pixel itself. So the intensity of the pixel could be a feature itself. So I could go to any pixel in this image and say that the red, green and the blue values of the intensity channel are a feature. Or you could do something more. So maybe you could compute some kind of index on top of this. So some metrics using nearby information. So for example, if you go to this pixel and say, my value at this pixel is not just the value that you see at that pixel, but an average of what you see in the neighborhood. Or any idea that you have. So maybe you detect the edges in this picture. And so whatever you derive from the raw data is called as a feature, and the hope there is that once you compute these features, it's better than just using the raw data to discriminate between, say, class 1 and class 2. Right? So what we have till now is that in our problem, we want to classify the data into k classes, and we are given what are called the features E, which are derived from the data itself. Right? And the problem of classification is basically we want to learn a function f that assigns a class given a feature E. So you are given a feature E. In this case, for example, E is the representation of the image that we saw. And given this E, we want to learn a function f, which then tells you which parts of the image are, for example, omega 1, so plants, omega 2, the soil, or so on. Right? In general, this could be k-dimensional. You could have not just plants and crops, but n number of objects in the environment, and you want to detect each one of these environments. Right? So as I told you before, this class will be only looking at the binary classification problem, but one way of thinking of this general k class problem is you could treat it as k binary classification problems. Right? So for example, if you have in this room tables, people, light, walls, for example, right? So one binary classification problem could be tables versus everything else, right? So this would include lights, walls, people, and everything. Another classification problem would be people versus everything else, right? This way, we can form k binary classification problems, and from this, essentially get all the k labels given the data. So the technique remains the same. So if we know how to do binary classification problem, we can extend it to the one of k classes. Right? So again, the same example here. In this case, we have the raw data as the image. Then our features in this case would be just, say, the intensity values of this image at each of the locations. And the goal would, today's goal basically would be how do we come up with an f, so with a reasonable f, which given these features E, in this case the pixels, returns me the C, which is the class of each of the pixel. Right? So in this case, the C would take a value of either 1 or 0. 1 would be the case where you have the vegetation, and 0 would be the case where you have everything else, say the soil, basically everything else. Right? So this is an example from the field. But you also have examples, say in general in urban environments. For example, here, it's not really an urban environment, it's a song, I guess, but the idea here is to figure out which are the people in this image and separate it from everything else, cars, shops, and everything else. So what we want as output of today's lecture would be to figure out these green parts, which are the people in the image, right? So this is also, for example, a binary classification, because what we are doing is people versus background. So there are just two classes, right? But in general, it could be more complicated. We don't just want to distinguish between people and everything else, but we'd also like to know a bit more, right? So for example, given this image, we'd like to know that the parts down here are the road, so what you see in light pink. The ones in this darker shade of pink are the footpath. So where, for example, if you have an urban driving scenario, you would like to know where the road is, where the footpath is, and so on. You'd like to know where the cars are, you'd like to know where the people are, and also, for example, you have these signposts all around the roads which you like to detect and use in whatever application you have, right? So this is an example of a multi-class problem, since you have cars, roads, pedestrians, street lights, and so on. Right? So both of them are classification problems, and we'll basically see how to tackle these. Right? So another rather classical example is the one that comes from what is called as the OCR, or optical character recognition. So if you write a letter to somebody, and on the envelope you write the name, and then you also write the PIN code. Right? So often the PIN codes are not read manually, but there's a machine which basically goes through the area where the PIN code is expected to be, and it has to figure out what the number on this, what the PIN code is, and you want to determine directly using your image without any humans involved, right? So it's not just for PIN codes, so not just numbers, but it could also be letters and so on. Right? So if we look at this problem, the raw data is, for example, let's say the pixels of the letter or the number that you want to figure out. Right? Then say you digitize it, and then say, for example, you have a number, and then you break it up into an image of, say, 20 pixels cross 20 pixels, and each of the pixels is either there is something written there, then it's black. If nothing is written there, it's white. So this is kind of the raw input that goes to this classification system, and the classification system should then figure out what this character is. So in this case, it's an A, and it does figure out it's an A. And what you see here is basically how the insides of the classification looks like in terms of probabilities. Right? So what you essentially want to compute is the probability of the class given the vector. Right? So given the feature vector. So in this case, you know the feature vector, which you could think of the values of this image. So what you could think is that, say, these are zeros, and say the black ones are ones, and say you have 20 cross 20 pixels. You convert this into a string, right? So something like 0, 0, 0, 0, some zeros, and then a 1, 1, 1, and so on. And this is a string of 400 characters, right? Since we have 20 cross 20 pixels. So this is our feature vector E. So the question that the classification system must answer, or what it must compute, is what's the probability that given this string, so this E, what's the class of those string? And the class is determined by omega here, right? So if it's, say, letters in the English language, this could be A, B, C, and so on, right? So in this particular case, what this does is it computes this probability, and it computes this probability for each class. So what's the probability that this particular data refers to the letter A given this string? So this is one probability. It computes the probability, what's the probability that this letter is B given this data, and so on. Right? So given a list of these, let's say 26 probabilities, the one which is the highest is the letter, is the class that this data is most likely to be. Right? What do you need in order to compute this probability? If you remember from the Bayes formula, you have two components, right? You have the prior component, and you have the likelihood component. Right? So what you see on the top is the likelihood probability. Right? So what's the probability that given this string E, what's the probability of this E given that this corresponds to the letter A? Right? So this is the likelihood probability that we had seen before, or what you get from the observation model. So you could think of this as an observation model. Right? So given that you know, or given that you have the character A, what should your data look like, right? And the other probability you have is this prior probability. What's the probability that the letter could be a itself? So for example, let's say we are considering an example where we just have letters, so no numerics, and then you know before you get the data that since the data has no chance to have any numbers, so the probability of whatever data you get being a number is basically 0, right? So there is a way that you can put in prior information about your world into this system, right? Also, for example, in many countries the postal codes are only numbers and there are no letters involved, right? So in this case you have a prior of what you're going to see, right? So if you have a classification system, it should use both the prior information and the likelihood information to figure out what the class is. So this is one kind of classification system, and we'll actually see a bit more of this in the next lecture, and we'll see a few other classification methods in this lecture as well, which are not dependent on this idea of a prior and a posterior kind of probabilities. And again, in this case, in this problem of the optical character recognition, the goal is again the same, how to figure out a function f which maps E, so our feature vector, into a class omega. Right? And we need to do this by using some additional knowledge of the priors, what's the probability of each of those characters to occur by itself. So no observations are involved here. This means that if you have, say, the letter, you don't even look at the pin codes, but you know something about them. So for example, if this letter is written somewhere in Germany, the postal codes are just numbers. So you know that there is no chance that there are any letters. So this is what will give you the prior probability of something, right? Or for example, you have a text which you want to determine what this text is. So you have, say you go out, you see some names on the shops, for example, you take out your camera, and then the mobile, for example, should be able to figure out what this text is, right? Very rarely, or at least I guess in some languages, the letter Q is not very often present. So it's very likely that the probability of Q is low. This is where the prior comes in. Right? Then the other part, which is actually a bit more difficult to define, is this likelihood probability. So given that you know that the letter is A, how should this feature look like? Right? This is a bit more difficult to define because everybody has, for example, their own handwriting. Somebody writes A in a way, somebody else writes another way. There's thousands of ways in which you could write the same letter. So to define this probability distribution of how the feature vector, the E, should look like given a particular character is quite difficult to manually at least describe. Right? So actually in this lecture, what we'll be spending quite a bit of time is how to learn these probabilities from the data itself. What this means is that you ask, say, 1,000 people to write the letter A, you collect the data from all the 1,000 people, and then figure out this probability from the data itself. So nobody says A has a slanting line from the left to the right, at 30 degrees, and from right to the left at 30 degrees, and a dash in between, whatever, and so on. So no rules are given, but just examples are given. So you basically just collect lots of data and then figure out what this probability should look like. Right? So this is the part where the idea of learning comes from. So we want to learn the probability distribution given the data and not really tell how this particular probability distribution is just by, say, thinking or just by having a model of what you expect to see. Right? So is this idea clear how we would get these probabilities, or why it's necessary to actually learn them rather than just specify this is the probability? Okay, I guess that's a yes. And right, so the idea, like I said, is to learn from data, not from rules, but from data, just because often it's very difficult to specify these rules. Right? So even in the simple letter such as, or a character such as A, there are thousands of ways. So for more complicated scenarios, like for example, you want to detect all kinds of cars when you go outside, there are, I don't know, thousands of models of cars. Although all of them have some things in common, they're all unique by themselves. They have some color, they have different heights, they have different shapes, and so on. So it would be almost impossible to cover all of these cases by specifying rules. But rather, if we show 1,000 cars, the hope is that we figure out how these probability distributions are, or we figure out a way to say that this is a car and this is a truck. Right? In some sense, this is also how we ourselves learn. So nobody ever told us every car that there exists. We just saw some cars, and even if we go to a different country or even a planet, and if we see something like a car, we know that it's a car and not a baseball or something like this, right? Okay, so then the idea comes of these examples. So these 1,000 examples that I was talking about. So these examples in the classification literature are called as training data. And training data has two components, right? So you have the feature, which could be the image pixels, and associated class. So somebody tells you what that picture corresponds to. So if you have a picture of a car, somebody says, say it could be a human, who says, what I see here is a car. What you do basically is collect lots of these data, right? So in this case, you collect n data points, right? So if you want to classify k different classes, you should collect data from k different classes and collect many examples of it. So the idea is that the larger the number of examples you have, the more kind of you could generalize how a particular object looks like. Right? So to do the learning, the basic thing that you need is the training data. And training data, at least written like this, are basically tuples. So tuples of feature and the corresponding class. Right? In this case, you have n training data, so n, let's say, features. So this is a vector which is whatever n cross whatever dimension, and for each of this vector is a class assigned. For example, is this the letter A? Is this the letter B? Is this the letter C? And so on. And the goal would be to use this data to figure out what the f is. So how to come up with this magic function f, which given a new e, so not just from the training data. So you learn from, say, thousands of cars, but then you are given a new car, or the image of a new car, which you have never seen before. And the idea is, can we come up with an f which is able to tell that this new car that you see is actually a car, right? And the idea is, while you learn f, you only use the examples that you have seen before, and you are able to generalize it to a new incoming data.
Does the picture have to be of only a car, or can it have background and told you all of that?
You probably should have the background, right? If the image is only car, then there is nothing to classify. Everything in the image is a car. You should have a background, and it could be any number of things. It could be a road, a people, or whatever. In the binary classification problem, your output should be that it's a car. Was your question about the training data itself?
Yes.
Okay.
The E would be the whole picture, and I would label the picture as car.
It could be both the ways. For example, a rough way would be you have an image, and say, let's say 60% of the area of the image is covered by a car. You can call that this whole image is a car. This is, let's say, one level of resolution. The another one is you do, say, the labeling at a pixel level. So every pixel that's a car is a car, and everything else is background. So it depends on the amount of effort that you want to put in during the labeling time and your application itself. So suppose it's an application, a mobile phone application, where you have just a static image and you know that there's just one main object, probably the first kind of training data where given an image, it's a car, given an image, it's a cat, is sufficient. But say if you want some more resolution, you want to know where exactly this car is, then you would need to have, say, a pixel-wise labeling. So this then basically leads to this idea of supervised learning, right? So supervised learning basically means that the classifier f, or this function f that you are learning, is based on some training data. So somebody has told how cars look like, and given that this knowledge you have to figure out how new cars could look like, or given a data what a new car is like. So here the knowledge comes from some expert. This expert can be often humans giving labels, right? So the opposite of supervised learning would be the unsupervised learning, which essentially means that the algorithm or this classifier f should by itself figure out what different parts of the environment are, right? So both this lecture and the next lecture will be focused primarily on the supervised part, and the last 1 or 2 lectures will be on the unsupervised part. So all the examples that we'll see today would be where we know a set of examples, we have this training data, and then we need to figure out from this training data what the class of the object is. Right? Yeah. So the main problem in this, the main question that we have today is how to come up with this f that works well not just with the training data but with new unseen data. Right? So if you give me lots of images and with cars and tell me that there is a car in this and lots of other images and say that there are no cars, maybe I come up with an f which works very well for this example set. Right? So you show me 100 images, I come up with an f which works very well with this 100 images, but then you give me a new car, say of a different color than seen before, and my entire system fails. This is a bad classifier. So what we want to design is a classifier which works well for new unseen data, and we'll see how to basically do this both in this and the next lecture. Right? So just for nomenclature's sake, you would come across these two words often in textbooks, for example. Classification and regression, both are very closely associated. So classification is the problem where the output of the classifier is a label. So it would either say car, no car, plant, no plant, or something like this. Whereas regression is also actually a very similar problem where you want to still estimate f, but the output could be a continuous variable. It's not just car or no car, but in a sense it could give you, say, the value of a particular property. For example, say you want to predict the price of the car. So somebody shows you an image and you need to predict the price of this car. Right? So your training data would be, let's say, sizes of the car and let's say the engine power of these cars, and you have some knowledge of what the prices of these past cars were. Right? Then what you would like to know now is actually a euro value. So this particular car costs 10,000 euros. Right? So this is a continuous problem. Right? It could be 10,000, it could be 10,001, 10,002, or whatever. So this kind of problems are often classified as regression. In this lecture, we'll primarily see classification algorithms. Many of the algorithms which are used for classification can also be used for regression and vice versa, but we'll focus mainly on the classification problem. Right? Okay, so let's see another example. It's one of the classical examples from the book by Alpayadin, which is a very good, let's say, at least introductory book for machine learning. And the example is like this. So you want to figure out which one of the given some data, you want to figure out whether it's a family car or not. In this case, there are two parameters. So the price of the car and the engine power. So given these two information, so in this case our E, the feature vector, are these two values. What's the price of the car and what's the engine power? Right. So for example, one car could be 15,000 euros with 50 kilowatts of power. Another car could be 20,000 euros with 80 kilowatts of power, and so on. Right. So you have these features, this E, which represents a car. In our case, it doesn't matter what the color of the car is, but just the price and the engine power. Right? So it's a decision that we have taken that our feature vector has these two components. Nobody stops us from adding the color itself as well, right? So maybe somebody thought the color of the car doesn't determine whether it's a family car or not. And they thought that these two features are what determines whether a car is a family car or not. Right? Then, since it's a supervised case, we have these labels. In this case, you have the feature vector which gives the price and the power, but you also have this extra information which is true or false, which is actually the label for this car. So if it's true, it means that a car which costs 20,000 euros and has 80 kilowatt of power is actually a family car, whereas the ones which has false says that this is not a family car. Right? So you ask whatever 100 people, and they tell you these things. My car is this much, it costs this much, it has this much power, and I consider it as a family car or not. The question then is somebody else, a new person comes and asks, my car costs 12,000 euros and has 65 kilowatt of engine power. Is this a family car or not? The goal of this classifier, or the aim of the classifier, would be to tell is it or is it not, given that you have a set of previous examples to use as reference or use for learning the model. Right? So if we actually plot this data, this is how it looks like. So on the x-axis, you see the price of the car. On the y-axis, you see the engine power. So these are the two components of the feature vector for each car that you had. And each of these circles that you see is one of the data point. Right? So whatever, this one has this much of price and this much of engine power and so on. Right? Then you see either a positive sign or a negative sign inside the circle. The positive sign means that this is a family car, and the negative sign means that this is not a family car. So essentially, this is the learning or the training data that you have. And given this data, your classifier needs to tell if a car comes up here, is it a family car or is it not? Right? So basically, yeah, like I said, these are the negative examples, the positive ones, and the question then the classifier needs to ask or needs to answer is basically make a decision, right? Okay, so what would you think, seeing this image, what would you say is a reasonable class for something that lies, for example, here? Or do you have an idea, given this information, and I ask you the question, if a car lies somewhere here, or the feature vector of this car lies somewhere here, should it be a family car or should it not? Okay, maybe is a good answer, but what would be a strategy, for example, to figure out if it's a family car or not? So how to come up with this F? F is basically, you could think of it maybe as a set of rules which say, okay, if this happens, then this is a family car. If this happens, it's not a family car. Could you come up with, just by looking at it or just by guessing, what could be a way to figure out this F, or what would be this F?
There are a bunch of strategies.
Okay.
Strategies.
Okay.
So we could do like a square or extend like a circle around the points or whatever.
So you say that I see some pluses here, I fit some kind of shape around this F, and then based on this shape you would, yeah, this is one of the strategies. So figure out a shape which best explains this data here. Right? What could be a really trivial one? So if you would go and if you were to just decide, what would you do? So suppose something falls right here. Right, so you would see how close is it to my training data, right? So if a car previously had this cost and this engine power, find the example from your training data which is the closest in terms of both engine power and price, and you say, okay, this may be a reasonable class for this new classifier. Right? This is often called as the nearest neighbor classification, and we'll see how this works. In terms of shapes, one of the shapes that is quite straightforward is, let's say, a box, right? So you could come up with a box. Essentially what this box says is that if the price of the car is greater than some value and it's less than some other value, and the engine power is greater than some value and less than some value, I consider this as a family car, right? So this is a kind of a decision tree, right? So you make decision based on some questions. You ask, is my car more than, or does my car cost more than this number of euros? Does it cost less than this number of euros? Is the engine power more than this and less than this? So you have certain questions that you ask, and based on the answers of this question, you say, okay, if it falls within this range, it's a family car, otherwise it's not. So these kind of classifiers are called as decision trees, and this is also something that we'll see later today, how to design a decision tree. Right? But the thing is, this is not the only box that you could draw. Right? You could draw any number of these boxes that you see here. Right? So all of them agree with your training data. So take any one of these black boxes, right? So all the examples which are a family car are inside of this box, and all of them which are not a family car are outside of this box. So in some sense, all these boxes kind of explain your data quite well. Then the question comes out, which one of these boxes, essentially this box is the classifier. This is the F that we're looking for. Right? So which one of these boxes is the best box in a sense, right? And there are two boxes, let's say, which are special boxes. The one which is towards the most outer boundary. So if you move this box any wider or any taller, you would end up making a mistake in your training data itself. So this often is called as the most general hypothesis, or in this case, the most general box. So it consists of all the examples which are positive and also properly classifies ones which are negative, but right at the boundary. The other boundary is the one which is the most specific case, which just draws a very tight box along the positive examples. Right? Both of these are valid Fs or valid classifiers. And so then the question comes, which one of these boxes should I consider? Right? So in general, you have the most specific box S and the most general box G. And the question that that one must answer while choosing F is which one of these boxes. So a general box is called C, and often this is called as version space. So which one of these version spaces works best, right? So it should not just work best for your training data, but in general, it should work well for any new data that you are going to see. So if you see a picture of a new car, this C that you choose should also be good for the future points that you have, right? So of course, if you have no prior information, let's say one of the best decisions you could make in this case is a box which is somewhere in the middle, right? So it's neither too tight nor too wide, because if you choose a box which is too tight, maybe it doesn't work well for new unseen examples which say just lie right next to this box, right? In that case, you would classify them as not a family box if you were to consider this tight box. Whereas if you consider this most general box and an example lies really at the corner, then you also make the mistake in the other direction. So given, let's say, no additional information, one way to fix this box is what's called as maximizing the margins. Essentially, it means find the middle ground in between these two boxes. And so margin is somehow the distance between the edge of the box to a positive example and the same point to the negative example. So the idea is you would like to move, for example, this line here such that the margin is minimized. Right? Okay, so now we have seen, or we have an idea of what the problem of classification is, particularly binary classification, and let's say what's involved in learning a classifier. Before we actually learn the classifier itself, we will see how to actually characterize the performance of a classifier, or in some sense, what are the metrics through which you could say, okay, this is a good classifier, whereas this is a bad classifier, right? So we take the same example of this family car thing with the price and the engine power, and say there is an oracle which actually gives us this true box. So somebody tells us this is actually the box which is the correct box that one should learn. So in reality, so in real applications, we don't have access to this box, but let's say in this case, this is the correct hypothesis. The green one is the correct hypothesis. Then you go home, you build your own classifier, which gives you this box, right? Now, given this box, and you know that the ground truth hypothesis or the actual hypothesis is this green box, how good is your box compared to the ultimate box that there could be, right? So as you see, there are portions where you do not predict correctly, and there are portions where you predict the labels wrongly. And these two areas have specific names, what are called as false positives and false negatives. False positives means these are those examples or the labels for those points which you say that it has this class 1, whereas it actually is class 2. Right? So it's the examples which you wrongly recognize as cars, for example, in this case, family cars. False negatives are those ones which you miss. So any sample that falls in here is actually a family car, but you are not able to detect it as a family car. So these are the two main kind of errors that you could make. And if you actually look at all the possible outcomes, there are actually 4 possible outcomes for a given sample. So if you ask the question, given E, you give me a class, there are actually 4 possible outcomes. The first one is the best case, what is called as a true positive. So the car is actually a family car, and our classifier says that it's a family car. This is the best possible case, right? So we want a true positive rate of our classifier to be as high as possible. Then the next one is what we saw before, is the false negative ones. So in which case a family car is wrongly classified as a non-family car. So it's this area, right? Then the third part is what is called as true negatives, which means that a non-family car is actually classified as a non-family car, which essentially comes out to any examples that are outside here. So everything here is not a family car, and our box, the red box, says that it's not a family car. So these are the true negatives, right? And then the fourth part is actually the worst kind of ones, which are the false positives, which means that it basically belongs to this area where it's actually not, or a non-family car is classified as being a family car, right? It's probably not correct to say it's the worst, but it's as wrong as, let's say, the false negative ones, right? So this was for the car example, but this works in general for any binary classification. And so basically, true positives is where all positive examples are classified as positives. True false negatives, where all positive examples are classified as negatives. So we want to, ideally, we want to design a classifier which reduces the things in red here. So the false negatives should be as low as possible. The false positives should be as low as possible, whereas the true negatives and the true positives should be as high as possible, right? So for a binary example, you can also arrange it in the following table. So what you see on the left is the result of your classifier, your box. So given an example, your box says, is it positive or is it negative? Whereas on the top axis is what the actual data itself in reality is. Is it positive or is it negative? Right? So it's the same information that we saw in the previous slide, but just put in a table format, where you have the true positives here, the true negatives here, and the errors on the cross diagonals. Right? Okay, and there are some special names for it, both in English and in German apparently. False positives are called as type 1 errors, whereas false negatives are called as type 2 errors. So based on the kind of literature you would read, sometimes false positives would also be called as type 1 and false negatives as type 2. So you probably also know this under the name of confusion matrix. So what we draw is also called as confusion matrix. As the name suggests, it's how do you somehow confuse a class with all other classes that are there. And in the special case of binary classification, the confusion matrix basically is a bit simpler in the sense that the true positives are the places where you classify class 1 as 1, and also the true negatives are the ones where you classify class 2 as class 2, and whereas the diagonals are one where you make the errors. So you say class 1 is class 2 and class 2 is class 1. Right? So this is the specific case in which the classes are binary. Right? So in general, if you have many cases or many classes, you could have, you use the terminology of true positives and true negatives instead. So this slide here is mainly for reference. So based on these 4 values, people have come up with several metrics which characterize how good your classifier is. So the reason that there are so many metrics is based on the application that you have, different values are more important to you. Right? So again, what you see in these 4 boxes are what we saw in the previous slide. These correspond to the true positives, the false positives, the false negatives, and the true negatives. So the 4 possible outcomes that a classifier can have. And then based on these values, you could compute different things. For example, you could compute what is called as precision, which is sum of all the true positives divided by the sum of all the outcomes that are possible. Whereas similarly, you could compute what is called as sensitivity, which is also in some literature called as recall, is sum of all true positives divided by the sum of all conditional positives, which are essentially the sum of this column here. So what you see here is if precision sits here, it means it's this guy divided by both these columns. So each one of these rows and columns corresponds to a specific metric that you have. And the metric that you choose to evaluate your classifier depends on the application. For example, you have an application, say, of detecting pedestrians in an urban environment. And say it's very, the requirement is that you detect all the pedestrians that are there because it's important that you don't hit them. But it's also okay that sometimes if you say some of the posts that are there along the road are also pedestrians. You make some mistakes calling some poles as people, but you really want to get all the people there because this is important for your decision of how to drive and not to run into either poles or people, right? So in that case, you would like to design a classifier which is sensitive or which has a high recall value, which means that you get all the people right. Maybe you also get some poles as people, but you are quite, your recall rate or your sensitivity is quite high, right? You could also come up with another example where you don't care so much about the recall, so you don't care that all the instances of that object are recognized, but you care that if you recognize something, it's actually the correct one, right? So then you would try to increase your precision. So say there are whatever, for some reason you want to be really precise that your image is one of a cat, right? So you want to make sure that if you say something is a cat, it really is a cat. And this means that you have to make sure or design a classifier such that your precision is high. Maybe you miss lots of cats, but the cat that you say is a cat is really a cat, right? So depending on your application, you try to maximize or minimize one of these metrics, right? So it's mainly for reference. So whenever say you are working on some classification problem and you want to evaluate how this performs, you could come back to here, compute all these metrics, and then decide, okay, does this fit my application or not? Right? So this a summary from what we saw before. So this false positive rate is defined as the number of false positives divided by the false positives plus the true negatives. So this sits in one of the columns here. Right? And similarly, you have this recall, which tells you how many true positives there are with respect to the number of true positives and the false negative. So it's a bit confusing, all this terminologies. So whenever you want to compute it, just come back to this slide, see the columns and the rows, and then you can compute the metric that you have, right? So another way to look at this metrics is through a curve that is often called as receiver operating characteristics, or I think also relative operating characteristics. This kind of summarizes some of the properties that you saw in the previous chart, this big chart that you had. So essentially what you do here is you make a plot of the false positive rates versus the true positive rates on the y-axis. And the goal is you want to have as many true positives as possible with very little false positives. So you want to make very little false positives, and you want to be right most of the time. So if your classifier is at this left end in this case, so your true positives are really high and very little false positives on this so-called rock curve, you would be towards the left end, right? So if you, the red dotted line that you see here is random guess. If you just randomly guess this is a car or not a car, your classifier would sit along this line, right? If you are below this red curve, it means that you're worse than random guess, so you're doing something really wrong. If you're above, it's a bit better than random guess, and the more you go to the left corner, the more better your classifier is. Right, so this is one way in which you could analyze the classifiers. So actually why you see a curve is because of the fact that your classifier may have some thresholds, right? So you say, for example, in the case of the box, you could change the height and the width of this box, and each one of these different boxes that you will have will give a different performance. So as you change the threshold, which in case is the height and say the width of this box, the performance of your classifier changes, and you would like to come out with that threshold which, for example, increases or is as high on this chart and as much to the left as possible. And then you say, okay, my requirement needs that I am at least I have a true positive rate of this much and I have a false positive rates of this much, and then you say, okay, I use this threshold for my classifier, right? So the name is a bit strange, but it comes for historical reasons. So it's called receiver operating characteristics because it was first designed to analyze detectors or radar systems which were tasked with the goal of finding enemy planes, I guess during World War II. So the idea was, I think the American Army or Navy, whatever, wanted to detect when the Japanese planes were coming. And therefore, a correct detection would be a positive identification of the Japanese plane, whereas a wrong detection would be either missing a plane or detecting, say, one of their own planes as a Japanese plane. And this is where the idea of receiver comes, because this receiver is this radar which receives the signal from the plane. But the idea remains for any classification system where you have to make the class 1 or class 2 determination. And so so this was one way of how to characterize how well a classifier performs. Another way to do this is through precision and recall, what we also saw in this chart. So precision is this true positives over true positives plus false positives. So this is somehow how correct you are in what you actually detect, and recall is how many of the examples that belong to class 1 are actually recognized as class 1. So based on these two values, again, you could draw a new set of plots it looks like the rock plot, so this receiver operating characteristics, but the x and the y-axis are different, so be a little bit careful. So on the x-axis is the recall value, which means if you detect, which means how many of the cars are actually detected as cars. So if you have a recall of 1, which means that all the cars that exist in your data, you actually say that they are, you actually determine that they are cars. Whereas on the y-axis is the precision, which is somehow how many of them were actually cars, right? And in this particular plot of precision versus recall, the best classifier is actually towards the right end. So if something has a precision of 1 and recall of 1, it's the best one. So it's opposite in this sense to the rock curve, where something on the left corner was the best, but in the precision recall curve, something on the right corner is the best. So the higher you are to the right one, you are quite best. So often when you read some papers or some textbook, you would see multiple one of these multiple lines. So for example, in this case, this is your method. So this is your new cool method, which outperforms everything that is out there, right? So you have, say, competitor 1, which is this blue guy, competitor 2, which is this green guy, and usually you want to come up with a classifier which lies over those other curves. So you want to be towards the right and to the top, right? Okay. So again, the fact that you have these curves is because of the fact that you have the thresholds. So as you change the thresholds, your classifier has different performances, right? The thing is, if you want, so all this is good, so this gives lots of information, but you then need to sit there and figure out, okay, what is my requirement, what is my recall requirement, what is my precision requirement, and then make a decision. There is another way to make this decision through just one number, and this is called as the F1 score. In this case, the idea is that you don't want a whole chart, but just one number which lets you determine, okay, is this the classifier that I want to use or not? And essentially, it's a harmonic mean of both precision and recall. It combines both the precision and recall of your classifier value and then gives you one number. And then as a designer of a classifier, you say, if my F1 score is so-and-so, I'm happy with this classifier. For example, I think the best F1 score is 1, so you can't have something that's more than 1, and the worst is 0. So you say, I have an application which requires a F1 score of 0.8. You see what's out there in the literature, and then you get the F1 scores and say, okay, this fits well for my application. So this is like one number reference to determine classifiers. Right? Okay. So till now, we have seen basically how to characterize the errors. So what are the different kinds of errors? What are the different metrics to say, okay, this is a good classifier or a bad classifier, or does this fit my application or not? So now we actually get into the part where we design a classifier. Right? So how to come up with this F. Right? So we came up with this box before. It was almost kind of arbitrary. Why just a box? We'd have put a circle or whatever. And what we would be looking at is two methods today. Basically, how to design a classifier, what are the main steps that are involved in designing a classifier. So like we saw before, since this is a supervised case, you start out with collecting data and then labeling them. This means you take thousands of images, ask somebody to say if it's a car or it's not a car. Right? So this is the first stage. Then, given these labels, you need to figure out some features. So this E vector. Right? One of the features could be just the raw, let's say, the pixel values, the intensity values, but maybe there's something more smarter that you could do. For example, maybe you look into the gradients of this image or look into the edges of this image. It has some more information, right? So based on the edges of the object that you're trying to recognize, this gives you an idea, okay, does this look like a car, or this shape doesn't fit at all, right? So this is kind of the place which, let's say, human intuition is required, or some brain power is required, where you have to think, okay, for my task of saying that this is a car, what do I think are important metrics? Is the color of the car important? Is the shape of the car important? What else is important, right? So this is how you design the features. It is very application specific, right? So it depends on if you're detecting plants versus weeds, or cars versus trucks, or something like this. Right? Then finally comes the learning part. So given these examples and given that you know, okay, this is something that determines my features, the E vector, how do I learn the distribution of features for a particular class, right? So say you have a car, how should these features look like? So either you learn this probability distribution, this is one way to make the decision, or the other way to make the decision is you don't really learn how the features are distributed, but you just rather learn a rule or what is called often as a discriminant function. So a function which takes in the E and says, okay, this doesn't look like a car or this looks like a car. It doesn't explicitly compute the distribution of the features like we saw in the OCR example, so the optical character recognition example, but rather just makes or just figures out a boundary between the two examples and says, okay, this is how I classify, make the difference between the two classes, right? So this step of the classification is called training, right? This happens even before you go out. So this is in your lab, you get your examples, you design a classifier. This is the first stage of a classification system. The next case of a classification system is what is called as testing, right? Because the thing is that you may come up with a F, you may design a classifier F, which is perfect for your training data. So it tells every car that's there that it's a car, and it has a recall rate of 1 and a precision of 1. So you have the best car detector that you have, but it only works on your 100 examples. As soon as I give you a new example, if it doesn't work, it's not a useful classifier, right? And the way to make sure that this classifier works not just for your training examples but for new examples is what happens in actually the testing phase, right? So you test your classifier on new examples, so not just your training examples and new examples, and you try this on different data sets and come up with those thresholds or those hyperparameters of your classifiers which you think then gives good answers on new data, on this test data. And so this test data should be one which are not used in your during your training, right? And then you evaluate the performance, which basically means you compute these precision values, recall values, or you make these ROC curves and then say, okay, this looks like something that can work for my application. Once you are done with the testing phase, then what comes out is the operational phase. Now you ship it out to your system. So maybe it's an app on the mobile phone, or it's something running on a car or something like this. So in that case, say it's an image, your camera takes the image, you compute the features the same way you did during your training phase, right? So if you computed edges, you compute edges again. If you computed intensity differences, you compute the intensity differences again. So it's the computation of E. It's the same as in the training phase. And then now, since you have learned this classifier F, so you could think of this as this red box. So you now fixed your red box. Use that red box to make a decision. This is online in the sense that you get an image, you use your red box information, the classifier F, and says it's a car or not. This is the operational phase of the classifier. So these are the three phases: the training, the testing, and the operation phases. Right? Right. So this concept that I was talking about of how well it does on new examples is what is called as generalization. Right? So for example, in this case, what you see here are training data. So on the left you see our training sets. So on the top you have lots of images of apples. You have lots of images of, I guess these are pears, tomatoes, cows, dogs, and horses, right? And somebody said that all these are apples, all these are pears, and so on. And this is your set of training data. Then somebody else comes up with a new apple, right? It looks roughly the same as the apples that you have seen before. So this box that you learned, or this classifier that you learned, should work well for this new training data, or new test data, sorry, which you have not seen before, right? So this measure of how well your classifier performs for the test set, which you have not seen before, is called as generalization. So what you learned, does it just work on this guy, or given a new example which is roughly the same, are you still able to guess or not, right? So you should not expect that if this dog looks completely different than the dogs that you have seen before, maybe it says that it's a cow or something like this. But at least for a reasonable example, so this dog looks, let's say the color is fairly close to this and the size is close to the rest of the dogs, you should expect to design, or your classifier should be such that it says that this guy is a dog, right? So this is the idea of generalization. So, so there are a couple of concepts which are associated with generalization. These are called as, the first concept is called as bias, and the second concept is basically variance. And the way these work, or the way to think about this, is the following. So you come up with a model of your classifier. So in the previous example of the family cars, you said that my model of the classifier is a box, right? I will fit a box to my training data, and this box is my classifier. But what if the real underlying distribution is not a box but a circle? Right? So maybe the true thing that one could do is actually put a circle and not a box, right? Then the mistake that you do, because you chose a simpler representation, in this case let's say a box is a simpler representation whereas a circle is a more complex representation, the fact that you chose a model which is simpler leads you to make certain mistakes during the classification. This kind of errors are what are known as bias. So it kind of describes the difference or the average model over all the training sets. So how the average model over all the training sets differ from the true model, right? So these are mainly due to the simplifications that you make. Whereas the variance in some sense is the component where you say, for example, have a model that's very complicated. Say instead of a circle, you could use a curve which you could, I don't know, swiggle in any way possible. Then what you could do is that you fit all the examples very closely using a very complex shape, say a polygon. So not just a circle, now you are allowed to use a polygon, right? So using a polygon, maybe you describe your training sets very well. You somehow fit to the noise of the data itself and not to the trend. So the goal of a classifier should be that it should capture the trend and not the noise, right? And if you design a classifier such that it actually is too complex, it actually captures the noise, and this is often characterized by what is called as variance. So to see it more, let's say graphically, you could take this example. So the red dots that you have are the training points, and in this case you want to fit a model. For example, one of the models, say our classifier, is a straight line, right? So given these red points, say this blue line is the best line that you could fit. Everything that lies above that line, say, is class 1, and everything that lies below is class 2. This is one way to fit a model, right? You could also fit something that looks like a parabola, like this green guy there. And again, something that lies on top is class 1, and something that lies on bottom is class 2. It seems in this case that this green line somehow captures the trend of the data better than just the straight line, right? So the error that the straight line here makes, due to the fact that it's too simple to explain the data, is what's called as bias, right? In this case, the blue one is biased because it doesn't really capture the entire trend due to the assumption that it's too simple. Whereas on the other case, what you see in the bottom here is, say, now you have this blue line which you are allowed, say it's a high polynomial equation where you're allowed to swiggle as much as possible. So you almost explain all the training points, say the red points, very well, but you really don't capture the trend. The trend is something like this. What you capture is the noise in the data, right? So the error the error that the classifier here makes is what is called as is captured by the variance, right? So it's the variance is really high here because it actually captures the noise in the data and not the trend in the data. So when you analyze a classifier, these are the two metrics that one should look out for, right? So if you see what constitutes towards the error of a classifier, you have these three terms. One is the noise in the sensing itself. So if you take an image there is some noise just in the act of taking the image, or there is some noise in the labels. So this is unavoidable. No matter what kind of classifier you design, you cannot reduce this unavoidable error. But you can always design a classifier or choose a classifier such that you reduce the bias and the variance. And if you saw the previous slide, you know that you can't arbitrarily reduce both bias and variance. They are somehow related. So if you have too simple a model, your bias will be high, maybe the variance is low. Whereas if you have too complex a model, your variance will be low, but the bias will be high. So you need to come out with a sweet spot where you are able to explain both the trend, but also not get caught up in the noise. Right? So with this variation, the bias and the variance also come these terms. Also comes these terms that you would see in the literature, what are called as underfitting and overfitting. So in the case where we tried to fit a straight line in this rather parabolic looking data, what we did was underfitting. So we used a classifier which doesn't have enough parameters to explain the data, whereas overfitting is one where we chose a classifier which is far too powerful, which has far too many parameters that it actually captures just the noise in the data and not the trend. So the goal is to come up with a classifier which is neither underfitting nor overfitting. We'll see a few ideas how to do this both today and mostly in the next lecture. Right? So there are some actually rules of thumbs how to do this. So usually the way to do this is first try a simple classifier, evaluate the simple classifier, and if you think that it doesn't match your requirements you have for the application, you go for a more complex one. So this would mean start out with a straight line. If it doesn't work, go with a parabola. If it doesn't work, go with a curve with power 3 and so on. Right? And the other trick is with the features. Right? So if you have good features which are able to discriminate well, it will always help whatever classifier you use. And so for example, initially you were only using the color of the car to determine whether it's a car or not. And then you say, okay, I use the color and the area of the car. Adding this area adds information which helps to determine whether it's a car or not. So one of the ways to improve the performance is to come up with new classifiers which are discriminative. Of course, this requires lots of thinking because maybe the application is not so simple that you could come out with a new feature very easily. Right? Yeah, it's just a summary. So the things that one must be aware of is that no classifier is inherently better. It depends basically on the application and in general the generalizability, so how well it works on new examples. And the things that one must be careful for while designing the classifier is the bias and the variance of these classifiers. Right? So actually how to do this? So one way to take care that the bias and the variance are kind of good is to make sure that during your testing phase, so once you train your classifier, you have the testing phase. During the testing phase, you make sure that you test the classifier well for new unseen data. And one of the ways or heuristic ways that people do is through the family of tests called as cross-validation, which basically means that you have this training data, you have a large set of training data with some positive examples and some negative examples. So you have basically the data and the labels. Then what you do is you randomly split this data sets into two parts. So if you have 100 examples, you take 50 examples, you break them into 50 and 50. Then you take the first 50 examples and you do the training phase on just the 50 examples. Right? So you learn how this box looks like or how this F is based on 50 examples. And then you learn the F and then you test it. And then you test it on the remaining 50 parts, which means that you do the evaluation in terms of the metrics on the remaining 50 parts. Right? What you do then is you repeat this basically 5 times. And the reason to do this is that each time you randomly sample, you get a different configuration, let's say, of the input space. And therefore, the idea is that the classifier that you learn is not just fit to one kind of data, but at least fits your training data quite well in different combinations of it. And so people have done some experiments and come up with the idea that this 5 times split, so it's called this 5x2 cross validation, yields a good classifier. And so you may ask why 5 times and why 2? These are somewhat arbitrary, but there's some reasoning behind this. For example, if you do say 100 repetitions instead of just 5, it's maybe not much more useful, because when you draw from your examples randomly 2 paths 100 times, maybe many of the sets that you draw look the same, and it's not really useful to do 100 folds, for example, or 100 times, and so on, right? So basically, when you do this 5x2 validation, you end up with 10 classifiers, and somehow the classifier that you give out is the one which is in average the best amongst these 10 classifiers. Right? Is one way to make sure that the classifier that you design also works well for new data. Okay, so now let's move to the first kind of classification method, the nearest neighbor classification. This is one of the easiest way to design a classifier. In this case, actually, you don't really need to learn something new. The feature distribution is basically the training data itself. So in this case, you get a set of labeled data, the feature vectors and the labels. This itself is your model. What you then do is that given a new example, you just check which is my nearest training example and say, and look out for the label of this nearest example and say, okay, this is my label. For example, if you take this family car example, right? Somebody asked the question, what's the class of a car which is 10,000 euros and 50 kilowatt horsepower, right? Then you stored all your previous features during the training, then you look it up in this table. Okay, what is the one which is closest to 10,000 euros and 50 kilowatt? You fetch this example, check the class of this example. If it says it's a family car, you say, okay, my new example is also a family car. It's kind of a lookup table. Right? This is one of the simplest ways in which you could design a classifier. So this is an example from the remote sensing application where you have a satellite image here. I think this is a multispectral satellite image, which means that you have the RGB values and also the infrared values. And the goal here is to identify between 4 classes. Actually, I think this image is from Bonn, from Rheinau. And the classes could be, for example, you would like to determine what is the water, what's grass, what's shore, what's urban environment, and so on, right? So the question is, given this image, there are 4 classes, get me the class of a new pixel. So what you then do is that you label parts of the image. For example, you label this part, this part, this part, and you label parts of the image. And then you ask for a new part which is not labeled. For example, you ask for this part. Is this, or what class does this pixel belong to? Is it water? Is it vegetation, or what? What the nearest neighbor classifier would do is look up into the previously stored training data. For example, in this case, it uses the RGB and the NIR values. It looks up which are the closest RGB and the NIR values and say, okay, it seems like this is a vegetation pixel, something. Right? And so if you plot these guys, this is how it looks like. So this is the training phase. Right? So these blue ones, so you have 4 classes which you label during the training phase. For example, the green ones are vegetation, the brown ones are, I don't know, something else. The red ones are urban environment, the blue ones are water. So this is basically the training phase. Right? Somebody clicked on these images and said, this is all water, this is all vegetation, this is all urban environment, and so on. And basically the question then is given a new point. For example, if you ask, what is this particular pixel, say corresponding to this particular pixel here, you say, you put it in your feature space. In this case, maybe you have band 2 and band 3, which could mean, for example, you have the blue and the NIR information. You compute the Euclidean distance to all your known examples and return the class of the one which is the closest. Right, so for this example, the closest example is a vegetation example, and therefore you said this new sample that you asked me is actually a vegetation pixel. Right. Is it clear how this nearest neighbor idea works? Straightforward and I guess the most intuitive one. And another way to basically think of this distance is actually in terms of the discriminant function. Essentially what this nearest neighbor function does is figure out these blue lines, and what you see here is the red lines are the centers of these different classes that you have. So maybe this is land, water, urban environment, and so on. When you do a nearest neighbor classification, essentially what you have come out is some kind of boundaries which divide these different centers. And given a new example, if the example falls in here, in this particular region, then the label of that particular example is the one corresponding to this center. So what we saw before, you could equivalently think of it as coming up with a discriminant function, and often in literature you would come across this, what is called as a Voronoi diagram or a Voronoi analysis. However, there are some limitations of this thing. So for example, what if your data is not really perfect and there's lots of noise in there? And sometimes maybe it's just because of the noise that your class that you predict switches. And therefore, if there's lots of noise, just because of one bad example, you may completely make a bad prediction, right? And the other kind of limitation is, let's say, the space, right, in the sense of memory. Say if you have just 100 examples, you just have to store 100 examples and check against these 100 examples. But say if you have 1,000,000 examples, then you have to store 1,000,000 examples because this is your model, and then check against this 1,000,000 examples. So it doesn't scale very well, right? So at least the scaling problem will still remain, but the noise problem, we could kind of address it by, let's say, not just choosing the nearest neighbor, but let's say we say which are the k nearest examples. So 5 nearest examples, and then make a vote, right? So you have an example, you find the 5 nearest examples, 4 of them says they are urban environment, and 1 of them says that it's water. Then you can do a majority vote. Okay, since 4 guys says that it's urban environment or buildings, and 1 guy says that it's water, let's go with urban environment. So you could kind of counter the noise in your data by not just using the nearest example, but the k nearest examples, right? So this is the one way you could robustify it. Of course, now you have the task of also choosing what this k is. Should it be 5? Should it be 500? Should it be 1? What should this k be? And this really depends on the data distribution in the feature space itself, right? So if you use a really small k, maybe it's not robust enough to the noise in the measurements that you have. Whereas if you use a really large k, then it means that you're also going into the space of another class. And so if you say that take the 100 nearest example, maybe vegetation and ground has lots of overlap in there. And therefore, depending on how your feature space looks like, you need to choose k, and this is often not a trivial problem. So you did get some robustness to noise, but you have now the task of also determining what this k is. So yeah. Is everybody clear with this idea of nearest neighbors and how you could design one? So if I were to ask you, could you code a nearest neighbor classify in Python, would you be able to do it? You could call SciPy, but my question was, can you actually say go through the steps of getting the features, computing some kind of distance to the feature vector, and then determine, right? Without calling SciPy. Okay, the other method that we will talk about today is classification using decision trees. So in some sense, this is this idea of box, right? So when we made this box for determining whether it's a family car or not, essentially we were asking questions, right? So we asked the question, is the price of the car more than 5,000 euros? This is a question for which the answer is either yes or no, right? So And then the other question is the price less than 50,000? Again, the answer is yes or no. Then you can ask the question, is the horsepower of this car greater than some value? Again, a yes or no question. Then is it less than another horsepower value? Another yes or no question. So essentially the idea with decision trees is that you ask a set or a sequence of simple questions, often binary questions, which means the answer is either yes or no. And given these answers, you need to figure out what class does this particular feature vector E belong to. Right? So it's a sequence of questions, the answer to which is the class that you want. So in this case, the f may not look like a function with some formula, but rather a sequence of questions. Right? And the idea is like this. When you ask this sequence of questions, essentially what we do is that we split the feature space or the input space. Right? So when we ask the question, is the car more than 10,000 euros? You split your feature space to one side where it is and the other side where it's not. And each time you ask such a question, you keep splitting your input space. In this case, learning the classifier means coming up with that area or that split which you think best explains for a new example, does this example belong to this split or not. Right? So in the simple example of the box that we had two splits. One split in terms of the price and one split in terms of the horsepower or the engine power. Right? So based on this split, we came up with a box and said, if a sample lies in this box, it's a family car, otherwise it's not. Right? Of course, this is an easy example. In practice, you could have your feature vectors could not just be 2-dimensional, but 100-dimensional, 1000-dimensional, or whatever. And in this high-dimensional space, one must split the space such that you kind of generalize this, generalize the characteristics of this class well, right? And essentially, what this is a hierarchical approach because you ask one question after the other. So you ask the first question, you determine something. You ask the next question, you determine something more, and so on. And therefore, in this sense, it's a hierarchical data structure. And in this case, the data or the training step is not as trivial as what we saw during the nearest neighbor. It's not just storing all the training data, but we need to do some kind of learning, how to come up with these splits. Right? Okay, so if we see another example here, basically what you see here is some sets of squares and some sets or a set of circles. And the goal of this binary tree would be to come up with a split, for example, like this. Right? So this split on the right corner, which then separates your squares from the circles. Right? So in this case, you could see there are two questions asked. One, so for example, you have two features, one on the x-axis and one on the y-axis. The first question you ask is, does my data point lie to the right or the left of this particular point? So this is a threshold, say W10. Does my training data, in this case, say this is the training data, does it lie on the right or the left? This will give you a yes or a no answer, right? If something lies here, it says yes, I lie to the right. Here, no, I don't lie to the right, right? This is the question number one. Then you ask the question number two, does it lie above this line, say W20, or below this line? So given these two questions, you have broken up your input space into this particular area. And now given a new example, if something lies here, you ask the same two questions again, and then you say, okay, since it lies here, right of W10 and up of W20, this belongs to the square class. Right? The way to actually think of these questions is in terms of a tree. So let's see how this tree looks like. The tree has basically nodes. At the top is the root node, which is the first question you ask. And each of the things that you see basically in these ovals are what are called as decision nodes. So these are the places where you ask the question. Usually it's a simple binary question. And in this case, you ask the question, is the x1 feature greater than some threshold W10? If the answer is yes, you go towards the left branch. If the answer is no, you go towards the right branch. Right? What is inside this decision function or these ellipses are often called as test functions because it makes a test. Is it greater than something? Is it less than something? Some questions like this. Then what you see in the squares here are the leaf nodes, which means that you have determined already what's the class for this data point. There are no more questions to be asked. So everything that lies here belongs to the class omega 1. So you don't need to ask any more questions. You're done here. So if you come to this part of the tree, then you know, okay, this particular sample corresponds to the class 1, and then you're done. Right? Okay, so is the idea clear? So if a new example is given, how do you determine whether it's class 1 or class 2? You basically start at the top. You check the first dimension of E, so this is the first feature vector, and you check it against the W10. This is during the test phase or even the operational phase. You look at the answer, you follow the tree based on what your answer is, and you should end up finally in one of the leaf nodes which will give you the answer. If you end up in this leaf node, it means that the question you asked or the data you gave belong to the class 2. If you end up here or here, it means that the class of the data you asked for is class 1. Right? Is this clear how it works in this tree? And basically, it's a different way of imagining the box. You could also think of this as drawing these lines along different axes of the box itself. Right? And so, like we saw in this tree, basically you need a decision node which implements the test function. This, of course, depends on what kind of data you have. Is it a greater than or a less than a question? Is it some other question where you check if this value is something? Is it a question where you check if the color of the object is green or something like this? Any question which has a simple answer, usually a binary answer. Right? So this is what the decision decision node should do. The function inside is called the test function, and sometimes it's also called as a split node because whenever there is a test or a decision node, you have a split. Right? So you split it into either new decision nodes or leaves. Right? If you reach the leaves, you're done. Right? Then come the leaf nodes. Basically, this symbolizes the end of the decision that you have to make. If you reach through this tree to the leaf node, then you don't need to ask any more questions. You know what the class of the example or the sample you have is. Right? And if you want to map this back to this idea of the box, essentially this leaf node corresponds to some area in the input space. Right? So you draw your input spaces, and each leaf node corresponds to some area in this box. Right? Okay, so just to describe the various steps involved as an algorithm. So you start at the root node, then you check if the current node is a leaf node. If it is, then you just exit. You're done. Right? So you know the class of your example. You don't need to do anything else. But if it's not, then you need to ask a question. Right? So perform the test of the current node and follow the corresponding branch. So if the answer is yes, go to the left. If no, go to the right, and so on. And after you do this, go back to 2. Check again if it's a leaf node. If yes, exit. If not, repeat this. So it's a recursive way to go through all the questions. And the output of this function, this recursive function, should be a class 1 or class 2. Again, I hope without using SciPy, you are able to implement this kind of if-else thing, right? Yeah. So what we saw is actually how to test the function. So given a new example, you could pass through this tree and say if it belongs to class 1 or class 2. What we skipped over is the fact how do we come up with these thresholds, right? So if we remember, the question would always say, is it greater than something, is it less than something, or is it some color or not, right? So this means that to build the tree, you need to know 2 things, right? One, what kind of questions to ask and what order to ask them, right? So should I ask first the price of the car, or should I ask first the horsepower of the car? In this case, it really doesn't matter, but in many other cases in which the input space is more complicated, the order of questions that you ask is important. And of course, you need to figure out what the value of the threshold itself is. And it turns out this is actually an NP-hard problem, essentially, which means that computationally it's really expensive to figure out what this optimal order of asking the questions is. And the only, let's say, the sure way to do it is to exhaust all the options and then to figure out what this correct optimal arrangements is. This works for small problems. If you have 5 to 10 questions, it's okay. It's, let's say, 2 to the power of 5 or 2 to the power of 10 combinations, and you could do it. But if it's anything bigger, any real world example, you would have millions of features or thousands of features, and it basically becomes computationally not possible to come up with an optimal arrangement of these questions, and therefore we need to use some heuristics. So heuristics are basically guesses which give you, let's say, not the optimal solution, but something that's close to the optimal and something that we can live with, right? And the questions would then be how to come up with a strategy which gives us good splits, right, without enumerating every possible order of questions and then figuring out what's the best. So can we come up with a trick or some idea which gives us a way how to make the next split, right? And there is one idea that is quite popular in decision trees, is this idea of purity, which essentially means that when you ask a question, you split your input space into 2 parts, right? So the yes part and the no part. And the idea here is that you should ask that question which results in pure children, in the sense that the 2 parts that you make constitute mostly of one class or the other. So you ask a question, is x1 greater than 10? Right? You can also ask the question, is x1 greater than 15? You can ask the question, x2 greater than 5? You can ask many questions. The thing that we are addressing here is what question to ask, and the idea here comes is that you should ask that question which keeps the purity of the next level, in the sense that the answer to this question should break up the input space in which one side is almost entirely of one class and than the other side. And there are a couple of ways in which this purity, or the converse is the impurity, is measured. One of the ideas is the entropy, and the other is called Gini index. We'll basically focus on the entropy idea today. So this idea of entropy comes from information theory. So if you've come from electronics and communication background, you probably would have seen this measure. So the entropy is defined by H. So the entropy for some area, so here sigma actually means some area in the input space, so some box. So what's the entropy of a box? So the entropy of the box is the probability of the class I multiplied by the log of that probability, and then you sum it up over all the classes. So if you have a binary class, you have binary problem, you have 2 classes, omega 1 and omega 2, essentially H of omega. So what's the entropy of this region, of this input space, is the probability of the first class times the log of the probability of the first class plus the probability of the second class multiplied by the log of the probability of the second class. Of course, there's a minus outside in there. And this is what you see on the y-axis here. Right, so what I've plotted here is, on the y-axis is the entropy, or this H, for a particular region omega, or capital omega, and what you see on the x-axis instead is the probability of, say, class 1 of omega 1, right? The way to read this plot would be if the split is such that the resulting members all belong to one of the classes, say in this case to class 1, we should have a low entropy, which basically means that if the probability of a sample in a split or in a region is, say, 0.05, right, then this means that the entropy of that value is something like 0.3, right? And vice versa. If you move to the other side, if the probability of class 1 is 0.9, which means the probability of class 2 is 0.1 because it's a binary classification system, it means that the entropy again is quite low because most of the elements of this region now belong to class 2. The worst case is to be somewhere in the middle. If the probability of class 1 is 0.5, it means that in the split, half of the elements belong to class 1 and half of the elements belong to class 2. And this is something we don't want. We want a split such that most of the elements belong to class 1 or class 2. So in this case, if you're not sure at all, it means that the entropy is very high. Right? So now we kind of have a measure which says how pure or impure is a particular split. And then the idea is kind of straightforward. So ask that question which reduces the entropy at each step. Right? So you compute the entropy at, say, before the split, you compute the entropy after the split, ask that question which reduces this entropy the most. This is the heuristic that we will use. And right, so this lets us choose this threshold. So the threshold that we chose, should the price be greater than 10,000, should the price be greater than 15,000? We should ask that question which reduces the entropy at every step. Right? If you look at the Gini's index, actually it's some, I think some mathematician called Gini invented this. If you look at the plot, the blue one is the entropy, the red one is the entropy index and the blue one is the Gini index. The shape of them are roughly the same, and for most practical cases they work similarly. So the idea is that either use the Gini index or the entropy. But the takeaway here is that you look into the change in this index, because basically entropy or the Gini index captures what's the mix of your elements. So how pure or how impure your splits are. And eventually you would like to reach to one, or you take that step which decreases this entropy or decreases this, decreases the impurity in general. Right? Right, now we know how to make the next split. The question then is when to stop. Right? One thing could be we stop when every one of the leaf nodes is completely pure, which means that whatever leaf nodes you end up with just have elements from class 1. Right? This is a reasonable assumption, and in some cases it will work out fine. But the problem is the data may be such, or the input space may be such, that going till the last value or making these splits such that the elements in each split is completely pure, which means with the purity of 1, may lead to overfitting. So you would carve out boxes or spaces in the input space which just explain very few examples, and they don't generalize well to new samples. And in that idea, with that idea comes let's say another heuristic, that you don't go till a purity of 1. You say, I repeat this process of asking questions till I reach, say, a purity of 0.8 or something like this. So you still have in your leaf nodes some mix, but you're happy with it because it explains the overall trend well without overfitting. Right? And just as a summary, basically decision trees are also kind of intuitive because there are a series of questions that you must ask. And the other advantage is that it works quite well in high dimensional data. So you could ask questions to each dimension and then kind of adapts well to high dimensional data. And also the nice part here is you could ask different kind of questions. You could ask questions, is it greater than something, is it less than something, or you could ask categorical questions, is it green, is it red, or something like this, right? So you could blend in numerical questions and other binary questions greater than, less than together to form this decision tree. Again, we saw that finding the optimal split is NP hard, so it's computationally difficult, and therefore we came up with this idea of making that split which decreases the entropy or which decreases the impurity. Right? Is it clear, at least roughly, the idea how to use decision trees to come up with a class for the feature vector? Okay, if that's the case, then I'll finish the lecture today here, and the next class we will look at a couple of methods which build on top of these methods and which are more robust, and some things that are actually used in the applications in the real world. Okay, thank you.